Yeah, thank you for the nice introduction, and thank you for having me here. So I'm Qinghua from Microsoft Research, and today I will talk about our work on partially observable reinforcement learning. So this is a joint work this is joint work with my collaborators Chi at Princeton, Alan Harvard, Pernice Google, and Chava from DeepMind. So I guess we all know reinforcement learning has many fantastic applications in recent years. There are some some notable examples, such as building the first superhuman AI that can beat human world champion in the game of Go, and also this OpenAI robotics, which can play this Rubik's cube almost as well as human beings. And more recently, people started to use reinforcement learning to fine-tune language models to better align them with human intents. And one way to classify different reinforcement learning tasks is based on how much information the agent can perceive from the environment. And by using this criteria, we can roughly divide those reinforcement learning tasks into two categories. The first one is fully observable reinforcement learning. So in these fully observable tasks, the agent or the learner can directly observe the ground truth state of the environment or the system. Examples are like all kinds of Atari games, the game of chess, and the game of Go. On the other hand, there are some other tasks where the agent can only make some noisy observation or only observe an incomplete part of the environment state. For example, in robotics, a robot may only be able to observe a limited part of the environment due to occlusion or due to the limitation of hardware. And also in healthcare, a doctor may need to recommend a treatment based on a limited number of measurements of the patient's body. And also another source of partial observability is noisy perception. So maybe you think you are dealing with fully observable tasks, but your measurement of the ground truth state is polluted by some noise. And in this case, you are still solving a partially observable problem. So if you talk to a learning theorist, or if you talk to a theoretical computer scientist about partially observable reinforcement learning, I think maybe the first thing they will tell you is, so partially observable reinforcement learning is intractable in the worst case. So on the computational side, even if I give you the model, I give you a toy model, and I ask you to do the planning to compute a good policy for this given model, it's like P-space complete. And even if I allow you to use an infinite amount of computation, solving a partially observable task with an unknown model requires exponentially many samples in the worst case. So these are all worst case hardness results for partially observable reinforcement learning. And they do not necessarily exist or apply to any of the real problems we are trying to solve. So in practice, there is this big contrast between theory and practice. So in practice, people have developed all kinds of very nice heuristics or approximate algorithms, which can solve many interesting problems quite well. So as a result, there is some gap between our theoretical understanding of partially observable reinforcement learning and what we can achieve in practice. And the goal of this talk is to identify some benign structures that exist in practical applications which make learning sample efficient. And okay, so before diving into the contents, let me make 2 quick remarks. So the first one is this talk is based on a theory paper. So another way to put it is most of the results I'm going to show you were derived by mathematical analysis. So I wish those results could complicate our understanding from empirical experiments. I wish they could offer something slightly new. And the second is, so before this talk, I was told most of the audience are from the empirical community. So I will try to include the least amount of necessary math. So throughout this talk, if you ever find any part unclear or unintuitive, so feel free to interrupt me and ask for some more intuitive explanations. Okay, without further ado, let's start. So to begin with, I would like to first introduce the most basic and fundamental model in partially observable reinforcement learning, observable Markov decision process. So in fully observable reinforcement learning, the standard model is Markov decision process. We have an environment, we have an learner interacts with the environment by taking actions. So at each time step, the learner observes some state of the current state of the environment. It then takes an action. Depending on this action and the current state, the environment will transition to the next state. And we repeat this process again and again. So this is like the standard model in fully observable reinforcement learning. The difference between MDP and POMDP is at each time step. So instead of directly observing the ground truth state of the environment, the system, the learner, the agent, it only receives an observation, which is emitted from the current hidden state. And all other parts are the same. Okay. And to make it a little bit more formal, we consider the episodic partially observable Markov decision process. So the agent interacts with the environment in the form of episodes. In each episode, at each time step, the learner first observes and receives an observation, which is sampled from a distribution conditioning on the current hidden state. After that, the agent takes an action, receives a reward, which we assume is a function of the observation and action. And then the environment transitions to the next state. And we repeat this process again and again. And the learning goal in POMDP is to find a good strategy, policy, to pick actions so that we can maximize this expected cumulative reward per episode. And throughout this talk, we will consider the most general scenario where all the model parameters are learner. Learner needs to identify a good strategy by interacting with the environment. So in other words, the only information the learner can gather is the observations and report from the environment. Okay, so a question about the definition, I will. Oh, go ahead.
Observation action.
Oh yeah, that's a great question. I think so. First, it depends on how you define your observation. So if you also include reward into your observation when you define the POMDP, then it could just be a function of your observation. And another way to think about this is, in practice, typically reward function is chosen by our researchers or engineers. So we want to define the reward function so that it is computable from what we can observe. So if it depends on the hidden state, maybe you cannot compute it, right? Because you cannot observe the hidden state in some scenario. Okay, is there any other question? Okay, nice. Sorry. Okay, so when I talked to my friends about POMDP, many of them will ask, why do we need an additional theory for POMDP? Why don't we just do some black box reduction to MDP and use whatever we have for MDP? So in some sense, they are correct, because if you view your entire history as a state, then effectively is an MDP. But the drawback of this view is because we know in POMDP the number of different histories grows exponentially with your decision length, your horizon length. If you solve POMDP using this black box reduction, then you will get a MDP of exponential size, and blindly applying existing MDP algorithms or theory may cause exponential sample complexity. Go ahead. Yes, yeah. Okay. So this black box reduction approach does not work. So some prior works they have tried to do some white box analysis of POMDP. So specifically, they are trying to exploit this hidden state structure of POMDP. And the way they did it is they try to identify the parameters of POMDP using some segmentation. So I won't go into the details of their approach, but this approach at a high level, it has two limitations. So first, model identification could be an extremely strong learning objective. So it can be much stronger than just learning a good. So for example, if any unreachable states, then it's essentially impossible to identify the model parameters corresponding to those states. But in this case, you can still learn a good policy. A policy doesn't care about those unreachable states. And additionally, many POMDPs, they may admit several different parameterizations. Or in other words, you may have two different sets of parameters which induce the same POMDP. So in those scenarios, it's also impossible to do parameter identification. Another limitation is this tensor decomposition of spectral methods. This method, it typically requires very strong eigencondition on the tensor. And as a result, these two limitations, their methods or their results only apply to POMDPs where your transition is full rank, your observation is full rank, your initial state distribution covers entire state space. So these conditions are, in my own opinion, are pretty strong, and they rarely hold in practice. So recall at the very beginning, we were saying we want to do something that can partially explain the practical success. So we want to do something slightly different, something can better capture what is really happening in practice. And to do so, the first step we took is to revisit those hard POMDP instances. So we look at those POMDP harness results, those exponential computation, exponential sample complexity results. And we try to see why those results, why those POMDPs are hard to learn. And at a high level, we found that the reason those POMDPs are hard because there are some like very important hidden states which have the same observation distribution. So in other words, the observations in those POMDPs, they do not contain a sufficient amount of information for the purpose of decision making. We can actually show that those examples are more or less equivalent to pathological tracking. It's like you enter a long sequence of digits, actions, and the only feedback you receive is whether your long sequence of digits matches certain underlying keyword or not. If it matches, you receive 1. Otherwise, you receive 0. So the feedback is extremely sparse and uninformative. But if we think carefully about those examples, we would find that those examples are actually highly pathological. So in practice, we rarely expect any algorithm to be able to break one password. And also, our observations in those tasks often reveal a rich amount of information about the surrounding environment of the system. So the natural idea is to, how about we just throw away all those pathological POMDPs, and we only consider the remaining POMDPs. So in our first attempt, we only consider those POMDPs where different hidden states have different observation distributions. This is sufficient because have like some different state mixtures, and these mixtures they contain dramatically different states. But together, these mixtures, they induce the same observation. So some naive example is a mixture over S1 and S2 could induce the same distribution as over S3 and S4, although S1, S2, S3, S4, they are dramatically different. So we want to further avoid these hard instances. So to this end, we introduced the so-called observable condition. And in short, it requires different state distributions or different belief states to have different observation distributions. And mathematically, it is for any two state distributions, two disjoint state distributions, we require their observation distribution to have TV distance at least alpha. So alpha is some positive constant. So by disjoint, I mean these two distributions, they are supported over very different states. So if one distribution has positive probability over state S1, then another distribution has 0 probability over S1. That's what I mean by disjoint. Okay. So several quick remarks here. So first, this assumption does not imply decodability. So it does not imply you can decode your underlying hidden state from your observations. So one naive example is here. So we have two states, two observations, and an emission matrix like this. And in this example, it satisfies the observable condition, but you can never decode your underlying hidden state. So another remark is mathematically, this condition is equivalent to saying your emission matrix has rank S. S is the number of different hidden states. Okay. And another thing I would like to emphasize is we put no restriction on the underlying hidden conditions. also we put no restriction on the initial state distribution. So it's only about the relation between hidden state and observation. Okay. So any question about this page? Okay, great. So okay, now we have this seemingly nice condition. So the next question we would like to ask is it sufficient for sample efficient learning? So to show you guys this is indeed sufficient, I want to first introduce a simple algorithm called optimistic maximum likelihood estimation. This algorithm is extremely simple. It builds upon two classic standard ideas from statistics. The first idea is everyone knows maximum likelihood estimation. So I give you a data set, and I ask you to estimate the model. According to the principle of maximum likelihood estimation, we should pick the model which has the highest likelihood over the data. And the second idea is optimism in the face of uncertainty. Let's say you're trying to decide between choosing two different strategies, and you are uncertain about the reward which strategy you're uncertain about the reward each strategy can bring you. And in this case, you should, according to the principle of optimism, you should pick the strategy that has the highest possible value. In other words, you always imagine the best thing will happen, and you make your decision in this optimistic manner. These are like the two ideas used in this algorithm. So how should we combine these two ideas to get this algorithm? So first, let's say we have a bunch of transition data collected from interacting with the POMDP. So first, we construct a confidence set which contains all the possible POMDP models which has high log likelihood over this existing data. So here, mathematically, we are just picking those models whose log likelihood is only slightly smaller than the maximum log likelihood. So this is not computationally efficient. And in the second step, we use the principle of optimism. We take each policy, and we use this model confidence set to compute the upper bound for the value under each policy. And after that, we pick the policy which has the highest possible upper bound. So yeah, this is like the optimistic planning step. And then we use this policy to collect more data, and we repeat. These are like all the details of the algorithm. So this algorithm is by no means computationally efficient. The reason I introduced this algorithm to you guys is I want to convince you guys there exists some way to learn observable POMDPs within polynomial samples. And we can prove that if you apply this algorithm to any POMDP that satisfies this alpha observable condition, then you are guaranteed to learn a near optimal policy with a number of samples polynomial in the number of states, actions, the episode length, the number of parameters, and this alpha observable parameter, alpha. And importantly, the sample complexity is independent of the size of your observation space. So you can apply this result to learning POMDPs with continuous observation space. So conceptually, this is a very nice theory result because it uses this simple generic algorithm to get some next guarantee for a fundamental model under clean and practical condition. So in the following slides, I'm going to show you why this is practical. Oh, go ahead.
Say the number of POMDP parameters. You're basically learning the transition matrix, the reward, but not the emission matrix, because that depends on the observation.
Oh, so okay. So in some case, okay. So here we are actually assuming the reward function is given. So we assume just reward function is known. It's something you maybe let's say it's something you designed, and we are just the model parameters are those in your transition matrices and emission matrices, just and also your initial state distributions. These three, like transition, emission, initial state distribution.
But then the emission matrix depends on the
So in the worst case, it can scale linearly with the number of observations. But in some scenarios, it might not be. For example, if your observation is your ground truth state plus some Gaussian noise, in that case, the parameters are just the mean will Gaussian, the mean and variance will Gaussian noise. So it depends on the task. In some worst case scenario, it could be. Yeah, I agree. Go ahead. They are we only assume they are bounded. They are bounded like 0, 1, between 0 and 1, or 0 and capital H.
Another assumption is you know the number of hidden states, like in the algorithm, etc.
Yes.
Is that common to make, or is there
I think we can do something like an upper bound for your hidden states, but if you don't even have an upper bound, I guess it's very hard to decide. Some apparent, some naive fix is you can do some like binary search, right? You just each time you double your guess over the number of states. But the difficulty of analyzing this modified scheme is you don't know when should we stop. So you don't know when we reach the true number of states. That's the main challenge. Okay, nice. And now let's discuss how practical this observable condition is. So first, it's pretty good. It's already like much weaker than what we had previously. And second, it can handle some actually observable tasks, such as noise detection, where maybe your observation is equal to state plus some Gaussian noise. In that case, we can show your in this this observable condition is in the static. But this condition can also have some very simple and annoying failure case. So let's think about this very tall example, simplified from robotic tasks. Let's say you have this cute robot. Its camera is facing the left, and the state is the animal behind it. It could be either a cat or a dog. But in this case, your observation, you can never distinguish these two different states using your observation, because your observation does not, your observation are the same in these two different states. So this is a very annoying failure case. And this is also something pretty common in practical tasks. So how should we fix some failure case like this? So maybe you can say, oh, let's add one more camera facing the right, and then the problem is solved. But it seems kind of too cheating. So we want to do something better. So okay. So one simple way to fix this problem is we can just rotate the camera and make one additional observation. So instead of trying to distinguish different hidden states using a single step of observation, maybe we can use multiple steps. And in this case, if we just rotate our camera, it will resolve the issue. So this motivates us to generalize the observable condition from single step to the multi-step setting. So previously, we were saying we want our observations to contain sufficient information so that we can distinguish different belief states using single-step observation. But now let's say we want to distinguish belief states using multi-step observations. And formally, we assume something like this. We assume there exists a probing policy such that starting from different belief states, you will get different observations if you follow this probing policy. So in the previous talk example, the probing policy is maybe turn around or rotate your camera. And in more practical scenarios, like maybe in navigation, this probing policy could be just walk around your house and rotate your cameras. Like if you are training a simulator, you could just add a additional meta action, which is to access the simulator state. So and the probing policy will just pick that special action to probe the underlying hidden state. And if you are thinking about healthcare, this probing action could be some more expensive, more time-consuming examination of human bodies. And in some like applications like TikTok or ChatGPT, you can just pop up a window asking for user feedback, and they may respond with certain probability, and they may not respond at all. And so similarly, we can use the same algorithm with minor modification to solve multi-step observable POMDP. So the first two steps are still the same. You construct the model confidence set, which contains all the reasonable estimates. And then you pick some policy which has the most optimistic return. And the difference comes in the third step. So instead of like passively following this policy to collect data, we interleave this policy with our probing policy to collect data. And by doing the intuition of doing so is we can collect more informative observations, which could be useful for us to learn some underlying state decoder or whatever. Okay, so I'd like to conclude the talk by some simple takeaway. So the first one is today we identified a simple condition called observable condition. It requires you can distinguish different belief states by looking at the distributions of multi-step observations. And any POMDP that satisfies this condition can be sample efficiently learned by some algorithm called the optimistic maximum likelihood estimation. And this algorithm is by no means computationally efficient. It's only a demo of sample efficiency. And these results, some inspiration from these results are like, when designing our partially observable tasks, we should try to make our observation as informative as possible. We want to ensure our observations are sufficiently informative to distinguish between different important states. And in addition, during training, we want to actively probe information about the underlying hidden states. We do not want to just blindly maximize reward. We want to gather information which is useful for learning some decoder function. And also, I would like to make some speculation about the limitation of purely model-free methods for partially observable tasks. So my intuition is like this. So in fully observable reinforcement learning, essentially we're trying to learn a policy or value function which tells you at the current state what action should you take, how much reward you can get. And in partially observable reinforcement learning, we have one more step, that is learning some decoder function, either like explicitly or implicitly. And for learning this decoder function, it's very important to notice that our observations contain a rich amount of information for this purpose. And if we could find a way to probe those information, to utilize those information, it could greatly speed up our learning efficiency. However, those purely model-free methods, they are mostly focused on learning the value equivalence, the reward equivalence. They are not utilizing this information to the best extent. So this might cause some efficiency issue in learning partially observable problems. And in theory, we can show there exists some toy observable POMDPs where model-free methods trivially fail. But if you add just a simple next observation prediction loss, it can fix the problem. And yeah, so that's all I want to say on today. Yeah, hopefully I said something useful, complementary to the empirical understanding.
I had a quick question. Can you extrapolate basically on how maybe some of these ideas work in the setting like of people using RL and LLM, and how maybe talk on the parser observability of like the LLM's past space?
Yeah, that's a great question. I can tell you some failure project I have done, which is kind of generalizing some of the insights in this project to language model. So one takeaway here is we should try to actively probe the information about the hidden state. And when training language models, you could also do something similar for language model. Let's say your language model takes in some demonstration. Like how does some in-context demonstration, like you give the language model some guideline about how to solve a math problem or a coding task. How does this demonstration inference change the internal state of your language models? And it's very hard to tell it by looking at the model weights or like some internal representations because they're extremely messy. And one easy way you can do it is you can actually just, okay, let's say I provide the model with some demonstration. I can just ask the model another new question. And I can check how good the model can answer this new question, or in what way the model will respond to this new question, conditioning on your previous demonstration, your data points. And by doing so, you can, in some sense, you can probe the internal state of the language model. That's some like loose connection between one project I have done and this one. Go ahead.
Talked about like interleaving the probing policy and the what if you're in a POMDP where there's like many states, and like not all the states are necessary for solving the POMDP task? Then it seems like the probing policy, like the data from the probing policy cannot be useful.
Oh yeah, right. Yeah, that's a great question. So, first, there are like two aspects. So first, suppose there are many states that are unreachable, or that can only be reached with an extremely tiny probability. Then essentially we can just extend our theory or our algorithm to, we can just pretend they do not exist. And so this is the first aspect. The second aspect is you are seeing like there there might be like some states which are different, but the difference doesn't matter that much for solving this specific decision-making task, right? So I think in that scenario, what you can do is, so first, this probing policy it's designed by you. So you can pick it to be some random actions. You can also utilize your domain knowledge to design this probing policy. That's like one possible way to avoid wasting samples. And another way to improve this probing policy is, or another way to avoid spending samples distinguishing non-important states is, there is this, you can generalize this paradigm to only focus on distinguishing those states which have different future dynamics. It's like you have two different states, but they will induce the future observations under any policy. So in that sense, although they're different in the past, but they do not matter that much for the future. So you can kind of ignore their difference. So there's many different ways to improve this sample efficiency part. But
I guess my general question is just like
how to automatically do.
maybe but maybe that's not that's not balance. But figuring out what the states are.
Yeah, that's a great question. Maybe you can consider something like value equivalent. Like you can, there's like some middle ground between value equivalence and like observation equivalence, right? So those purely model-free methods, they don't care about the dynamics, the observations. But in these like purely model-based methods, you try so hard to learn every single parameter. And maybe there's like something in the middle. Maybe you can do some like model-based approach in the representation space. So as some way of purifying irrelevant information. Just some.
Well, with that, let's thank our speaker.
Yeah, thank you for coming.